Am I audible? Hello.
Yes, sir.
Okay. Screen is visible.
Yes, sir.
Okay. Now today we will start with the transformer protection. Transformer protection. Transformer protection. So, as you already know, the transformer came in different shapes and sizes. That you will have the small transformer that you can place on the palm of your hand, and you have large transformers which are used for the extra high voltage applications. That is power transformers. The weight of the transformers it can be metric tons and occupy the large area. So various types of transformers which are used in the industry, we can write here the various types of transformers used in the industry. We can list them. We will have the generator transformer, which is used at the generator terminal to increase the voltage level for the transmission system. Then second, we will have the power transformer, which is used for the this application that is transmission system. Then we have the distribution system, distribution transformer, which is used for the distribution system. Then we will have pole mounted lightning transformer, which are used for the lightning purposes. Then we will have the grounding transformer. Then we will have the regulating transformer. Grounding transformer is used for the grounding purposes. Then we have the regulating transformer. Which is used for regulating the voltage. Then after that, we will have the welding transformer. In the welding transformer, the current required is large, so it is made like that. Then we will have the converter transformer, which is used in power electronics. Then after that, we will have the instrument transformers, that is CT and PT, which has wide range of applications. So if you see, now, if you see for a small transformer, let us suppose that we have a small transformer and the capacity of that particular transformer. Let us suppose that we have a small transformer and the capacity, that is the rating of that transformer is 100 kVA. Then we will have 11 kV, 440 volt. So this is a small transformer. Now, for this small transformer, the overcurrent protection in the form of the fuses can be used. Since fuse is providing the overcurrent protection, so overcurrent protection in the form of the fuse can be used in that very case. So this is a small transformer. Now, so for that, the overcurrent protection, which is fuse, is used as the overcurrent protection in that very case for a small transformer. However, if you take the case of a large transformer, let us suppose that we have a large transformer and the capacity of that large transformer is, rating of the large transformer is, let it be 250 MVA, 15 kilovolt to 400 kilovolt. So this is actually a generator transformer. This is the generator transformer, which is actually used in the large thermal power stations. And however, this transformer, if we are using the overcurrent protection in the form of the fuses, then it is not sufficient for that particular transformation, this transformer. And we need the elaborative protection system for that. We need different type of protection systems for that. We need the differential protection. We need the differential protection. Then we need the protection against the internal faults, incipient faults. Protection against internal faults. So these are also known as the incipient faults. Then we will have differential protection. Then we will have protection against the internal faults. Then we will have the overfluxing. If the flux is increased, overfluxing. And the cause of the overfluxing is the either the reduction in the frequency or the increase in the voltage, as you know from the equation of the EMF. EMF equation is given by 4.44 F phi. So from this you can say this overfluxing is there. It means the flux is directly proportional to the voltage. With increase in the voltage, we will have the overfluxing. However, if the frequency is decreased, in that very case, the same effect can be seen in that particular case. Now, second case is that we will have this protection, elaborative protection is required in that very case. Now, we will discuss the phasor diagram of three-phase transformer. Now, let us consider this diagram. Let us consider the three-phase transformer and various connections which are involved in the three-phase transformer that are star-star. Various connections which are used for the three-phase transformer is we have the star-star, then we will have star-delta, then we have the delta star, and then we will have the delta delta. Now from this you will see, as you have already read, that this will introduce the certain phase shift between the voltages and the current in the primary and the secondary side. So it will introduce the certain phase shift between the voltage and the current on the primary and the secondary side. And as a result, the CTs which are connected on the primary and the secondary side, they are also having different voltage ranges. So CT ratios must be different in both the cases. So we must see that what strategy we have to involve so that we get the no spill current. How the connection in the CT can be done in case of transformer, that so that no spill current would be involved in case of a differential protection if we are considering the differential protection. So which will ensure that during the normal load flow as well as during the external fault conditions, it will work well. So we can discuss. Before that, we will first discuss the phasor diagram. So how we can draw the phasor of that. So let us suppose that we have a transformer. This one is the primary, and this is the secondary. This is the star delta transformer. And in the star, let us suppose the current in the star side is IA. Then we will have IB. Then we will have IC. So this is the current on the star side, and on the this in this case, in this star that you already know, the phase current is equals to the line current, and in case of the delta, the phase current is not equal to the line current. Now we can do this analysis by considering this diagram. Now let's suppose that we will have this diagram, and we will draw, along with that we will also draw the phasor diagram of that. Now let us suppose that we have a three-phase supply, and we have a star and delta connected transformer, three-phase transformer. Now here we will see that the current which is moving towards it is IA. So IA is actually the phase and the line current, because phase and line current in case of the star are same. So here the current is IA in that very case. So what we do, we will draw the phasor diagram also along with that, so that you can understand the things well. So let us suppose we will have the current IA, and then we will have IB, then we will have IC. So in the three phases, these are the three phases which are 120-degree apart. Now this is the current which is flowing through this winding. Now opposite to that winding, the current is I. Opposite to that winding, it is IA. So opposite is I small a. This is caps A and this is small a. It means that, as we have seen from the dot convention, that these are in same phase. So the current IA in that very case, it would be this. This is the current IA, phase current IA. So the current would be IA up to this point. Then we will have the IB, that is this one, IB. Then after that we will have this current IC. So we will have the current IC. These are actually in the same phase. Now these are actually the phase current. Here, along with this phase, A phase, we will have this A. Then B phase, we will have this B. C phase, we will have this C. So these are connected in star and delta. Now we can find out the line current. So what is the line current in that very case? The line current is, these are connected in delta. So line current is this current and whatever this current is going. So this current is IC. So IA minus IC. In this case, the line current would be IA minus IC. Then the second case, we will have the IB and whatever is going here is IA. So it is IB minus IA. Then here we will have the IC and whatever going here is IB. So IC minus IB. So these are the line currents. IA minus IC, IB minus IA and IC minus IB. These are actually the line currents in case of the delta system. So how we can plot it on this diagram? On this diagram, you will see that we will have the IA. So if we consider the IA, then IA minus IC is this line current, this one. So this is IA and minus IC. We take the minus IC from here. So what we do? It is very difficult to write in. So this is IA minus IC because we have taken IA from here and we have taken IC from here, minus IC. So finally we are getting IA minus IC and this angle is 30 degree. Similarly, we can also draw for IB minus IA and IC minus IB. So this is IB minus IA here. This one is IA. So IB minus IA. And definitely we are getting here IB minus IA. And finally, IC minus IB. So IC is here. IB is moving like that. So we will have this. IC minus IB. So this is the phasor diagram that we are getting. Now, one more point is that as you see in the previous this diagram, you will see that this current IA, in that very case, this current is equals to IA minus IC divided by √3. That is the relationship between the phase current and the line current. So IA in this case is equals to IA minus IC divided by √3 that you already know in case of delta system. So this is how that you can draw the phasor diagram of that. What we do, what you have to do, you have to first take the phasor diagram. You have to see the currents on the primary side. Then on the secondary side, you have to see that what are the currents on that particular winding. So that is actually the phase current. Then we calculate the line current, and line current can be calculated from that. And in this way, you can draw the phasor diagram. So this is the phasor diagram of three-phase system. Now let us consider one more point that we have to consider while having the discussion about the protection of the transformer is the impedance of the transformer and what role the series and the shunt impedance plays in that. Now let us consider that we have the system. As you have read in machines that we will have the primary and the secondary, and the equivalent circuit is given by this. That is, we have the winding resistance and inductance and the magnetizing branch, and then we will have the secondary winding. Now, from this, you will see that the impedance of this is very large. Impedance of the magnetizing branch is very large. It is very large, and it can be seen that a shunt branch, this is the shunt branch which is representing this magnetizing branch. It accounts for the core loss and has the much larger impedance compared to the series branch that is combined this. So it has the much larger impedance compared to the series branch, and in the event of the short circuit, it is the series branch which plays its role, and it is the series branch which decides the short circuit current. because current is more when the impedance is less. So let us suppose that we have a voltage of 1 per unit, and then we will have the shunt branch. The impedance is 20 per unit, and the series branch it has 0.08 per unit. So since the impedance is very large, so current cannot flow through it. So if the current is flowing through this particular branch, and let us suppose the fault is here at that particular point, then definitely the fault current in that very case is given by V divided by the series branch. It is equals to 0.08 per unit, and its value is equals to 12.5 per unit. So the value of the current is very large in that very case. So this is the equivalent circuit of the transformer. And one observation that we have made from this equivalent circuit of transformer is that, sir, it is always in the during the fault, it is always the series impedance which decides the fault current, because the shunt impedance, which is the magnetizing branch, it has a very large impedance. So that is the thing that we have to take into consideration while making any fault, uh, while making any protection system for the fault. Now come to the types of faults in the transformer. Types of faults in the transformer. So transformer is actually subjected to the variety of faults. The most common type of fault is actually the winding to core fault. So it is the winding to core fault that takes place in the this transformer, and this winding to core fault is due to the weakening of the insulation. So this fault is due to the weakening of the insulation, winding to core fault. Then we will have the phase faults also in the transformer. Phase faults are also there in the transformer. However, they are rare and it takes place outside the transformer. Now, observation has been made. Some researchers have made an observation related to the distance of the fault from the neutral. So that observation we can discuss through this graph. Now this is a delta star transformer, and this delta star transformer, and in this case star is actually it is connected by some resistance. It is grounded by some resistance, and that is resistance. The value of the resistance in that very case is 1 per unit, and it has been seen that variation of the fault current with respect to the distance of the fault from the neutral. Now from this, what you have seen, you have seen that when we are there is a actually a relationship between the fault current increase in the fault current and the distance of x from the neutral. So as we are moving away from the neutral, the fault current goes on increasing on the star side and on the delta side. Here we will have the star side, and here we will have the delta side. However, let us suppose this is the case in which Re has some value, that is the grounding resistance has some value. However, if we are considering the solidly earth system, solidly earth means that no resistance is connected. In that very case, there is no relationship is seen in between the two. That we cannot have the direct relationship. You can see that it goes on decreasing on the star side, and however, there is no particular relationship on the delta side also. So for a solidly grounded system, you can see that there is no such a relationship has been seen. Now let us consider one more case. That is this case. This is the case in which we have used we have grounded the system. First, we have used the grounding resistance 1 per unit, and then we have used the solidly grounded system. Now, second is the case that we can discuss. And here we have considered the delta and the star system. Delta and the star. Now, in the second case, you will see that this is the actually we have used the system earthing transformer for the delta connected system. In this case, you will see that the minimum voltage on the delta side is at the center of the phase, that is the 50% of the normal phase. That is, you can see the minimum voltage is 50%, and if the voltage is minimum, then fault current is also less in that very case. So however, the range of the values of the fault current is less than that for a star connected winding. So this is a kind of observation that has been made by certain researchers. Now we can discuss the certain different type of faults that we were discussing. We discussed the winding to core fault, then we discussed the this phase faults. Then we will have the if we take the case of the power and the distribution transformer, they have the on load tap changing. So power and the distribution transformer. So they will have the OLTC, on load tap changing gear. So that is actually the another source of the fault. On load tap changing gear is there. Then one more point is that all the transformer are oil immersed. So for cooling purposes, all transformers are oil immersed for cooling. So there is the possibility that the level of the oil would be low in that very case, or leakage would be there. So the alarm must be raised and the transfer may be eventually shut down in that very case, that we can discuss. One relay is used for that, as Buckles relay is used for that. So one more point is that whenever we start the transformer, this transformer will experience the inrush during the starting. So the transformer will experience the inrush during the during the starting at this time of switching, and you cannot say that it is a fault. So we can have the relay such that it will allow that inrush during a certain amount of time, and it will not see as the fault in that very case. Then we will have another thing, that is interturn fault. Interturn fault is there. So interturn faults is actually the fault within the turns of the transformer, and however it will create the hot spot. It will create the hot spot within the transformer, within the winding. And however, if we see it from the relay, the current is not appreciable in that very case. So it can be this interturn fault, we can detect it by the non-electrical means. So we can detect it by non-electrical means. So we can detect it by the non-electrical means. Then that we have discussed, the overfluxing is there. One more issue that is the overfluxing. So overfluxing, it can be due to the increase in the. Then we will have the overfluxing. Flux is increased, that is overfluxing. So this overfluxing, it can be actually due to the under frequency operation or the increase in the rated voltage. So it will create the overfluxing issues. That is, it can overfluxing can also be observed whenever there is the increase in the voltage at the rated frequency. And the large transformer usually operate at their very high design limit. So overfluxing can have the dangerous consequences in that very case. So these are the issues that we can discuss one by one in the protection of the transformer. Now, first we can discuss the overcurrent protection. So first is the overcurrent protection. And now here you will see, as you have already read of the overcurrent protection in the previous lecture, you will see that we will have the two number of phase faults. We will have the two number of phase fault over current relay, and this is the ground fault over current relay that we have discussed in the previous lectures also. So this scheme is used for the over current protection. We will have the CT, and the over current relay is used as we have discussed in the previous lecture. Now, previous modules. Now you will see, as we have discussed, that for this phase faults over current relay, the pickup current value should be such that it should be greater than the maximum load current, so that it can have some overloading, and it should be less than the minimum fault current that we have discussed. So its range should be such that. Now, however, the pickup value of this relay, is actually uh, is uh, uh, is such that it will not. It is independent of the loading of the transformer. It is independent of the loading of the transformer. It is independent of the loading of the transformer. Now, what is the application of this overcurrent protection in case of transformer? Now, the application is that it is used for providing the overcurrent protection for the small transformer, providing the overcurrent protection for the smaller transformers, and it will act as a backup protection for the bigger transformer. So this is the case: smaller transformer overcurrent protection and backup protection for the large transformers. Now, this is the overcurrent protection. Now, another type of protection that is in case of transformer is the percentage differential protection. As you know, as it is aware of the fact that the two terminals of the transformer are very near to each other, so it is an ideal case for the percentage differential protection. So we can have the percentage differential protection that very case. Now, how we can distribute the currents, how can we can label the currents in that very case, that we can discuss in this case, in this percentage differential protection. Now, let us consider a transformer. We will have the delta star transformer. This protection is the percentage differential protection. So we will have the delta star transformer, as you have seen in this case. So what we do, how you can label the this currents in this type of transformer, how we can do that, we can discuss. Now, first what we do, we determine the instantaneous direction of the secondary winding current. So what is the first step? First step is direction of the secondary currents. determine. So we will have the transformer, and this transformer, this is the secondary current. Let us suppose that we determine the direction of the secondary current, that is IA. Then we will have the IB, and then we have the IC. Now, after this, the primary winding currents are determined. So we will have the IA, then primary winding currents are determined. That is IA. We will have, then we will have the IB. Then we will have the IC. Now, that is, we can write the primary winding currents are determined. So we will have the first we have the secondary winding current, then we will have the primary winding current. Now the currents on the star side are determined. Third point is the currents on the star side are determined. So this is the star side. So in this case, you will see that this is IA, then the current on the star side is same. We will have phase current is equals to line current in that very case. Now, this is the third step. Now we will have the fourth step. Line currents on the delta sides are determined. So we have to calculate the line current on the this delta side. Here the line currents are determined. Here we will have the IA, we have the IB, and then we have the IC. And you know that we have the IA here and IC is moving like that. So we will have, this is IC. So the final line current would be IA minus IC. Similarly, if you see that this current is IB and this current is IA. So final current, if we are adding IB minus IA with IA, finally we are getting the IB. So we will have the IB minus A, IA minus C, and IC minus B. So what we have done, we have determined the line currents on the delta side. Sorry, in the okay. Then we have written here, so no need to write. So we have calculated the line currents on the delta side. Line current on the delta side. Now from this, what we see that if we connect the secondary winding of CTs on both the sides, now here the CT is getting the line current, here the CT is getting the phase current. That is, it is phase current. In this case, phase current is equals to line current, and in this case, whatever CT is getting IA minus IC, and here the CT is getting IA. So in this case, what we see that if we connect the secondary winding of the CTs, this one and this one, in all the three phases on both the sides of star, then the current would not match up. How the current would not match up? We will have here, we will have the current IA minus IC, and if we are connecting the this CT, and here we have the spill current that is flowing, and here in this case we will have the IA. So from this, what we see, would see that this will not match up. So what we observe, that the currents would not match up and the spill current would result. So however, one observation can be made that if the secondary windings on the star side are connected in the delta, if we have the star side and the secondary side of this CT are connected on the delta, are connected in delta, and on the delta side the secondary windings are connected in star. In that very case, the line currents would match up with the line currents would match up, and finally we are getting the no spill current under the normal condition. So this thing can be taken into consideration, that what we have done, we have calculated the line currents on the both the sides of star and delta side. Then what we observe, after calculating the line current, we see that if we connect the CT on this side and this side, so finally we are having this current and this current, and these currents will not match up. And since these currents will not match up, so finally there is the spill current for no reason, even without any fault. So one observation can be made that if we connect the if let us suppose that we have the star side of the transformer and CT for the protection system, if we are connecting in delta and we have the this delta side transformer and CT that we have connected in star, in that very case the currents on both the sides would be same and there is no spill current. Now we can discuss this, that how it can be how it is implemented. So we can discuss this. Now, these are actually the connections of percentage differential relay under the normal load flow conditions. Connections of the percentage differential relay under the normal load that we discussed. Connections of percentage differential relay under normal conditions. So as per the conditions that we have discussed, we have seen that in the previous case, if we have the delta side of the transformer, and what we have to do, we have to connect the CT on the star side, CT as a star, and that is secondary of the CT as a star, and we have the star side of the transformer, we can connect the secondary of the CT as the delta. So that is, we have the delta star, then CTs which are connected in that very case would be delta and the star, that is secondary of the CT is delta and the star. So that convention you have to follow. Now you can see the different currents and how the spill current would not result in that very case. Now let us consider that we have this IA, the current which is flowing through this is IA. We consider this phase IA, then the current would be IA minus IC. Now this current IA minus IC is flowing through this, this is the line current. Now whatever reflected is IA minus IC. So this current is reflected on the secondary side of the CT. Now let us suppose that what we have assumed a 1:1 ratio of the this primary and secondary for the for study purposes. Now you see from the secondary we have IA minus IC. Now the current is which is flowing is IA minus IC. So this current is flowing from in this line IA minus IC up to this point. So we have considered up to this point. Now this point should also be IA minus IC so that no spill current would be there. Now we see in this case, you will see we will have C, the current which is flowing through this is IC. So this is the IC current which is flowing and it is reflected across this, that is IC. Now from this you will see when we have connected it in delta, then you see the current in the delta that is flowing is IA. So this current is IA, so it is connected at the C terminal. So finally we will have this IA minus IC. So this current IA minus IC, so it is reflected across this, and finally we will have the current IA minus IC, and here we will have AIA minus IC. So finally, two currents will match, and as a result, no spill current would be there. So this is the case. So what we have done for the primary side, if it is delta connected, we have used the secondary as a star and the secondary of the CT as the star, and in all the cases. And similar is true for the for other cases also. Like you have seen B minus A, then B minus A is reflected across here, that is B minus A. And finally, if you take the case of the B minus A, then we will have A and then B is moving like that since it is connected in delta. So B minus A, and finally we are getting this B minus A, and no spill current will result. So this convention should be followed, that on the primary delta side, we have the secondary of CT star, and on the primary star side, if the star side of the transformer is, we have the secondary, CT secondary as the delta to nullify that phase difference. Now we have set up the relay in that way. Now we have to see whether it will work for the external fault or it will act for the internal fault or not. That analysis we have to do, so that your understanding would be better in that very case. Now let us consider for the external fault. Let us do the analysis for the external fault. And the main idea is that it should not act for the external faults. So now let us suppose what happens, that fault in the terminal C, fault in the C which is outside the zone of the protection. So let us suppose that C fault is there. Now if the C fault is there, then overall IC is affected. That is, it is the overall IC is affected. That is, this IC is also increased and this IC is also increased. So overall IC would be affected because we will have the fault at C. Now, phase C. So this is IC. So since IC is there, so it is reflected across primary as well as the secondary. That is, this IC is also increased, this IC is also increased, and the CTs on the both the sides are also affected because of increase in IC. Now let us suppose that in IC is increased, so this IC is reflected across here. This one, this is reflected across here. That is, we will have IA minus IC. This is reflected across here, and this is also reflected across here. That in this we will have the IC minus IB. So this is also reflected across here. So the current in these two secondary CTs are increased. This one and this one, as shown in this dark color. So the current is increased. So to nullify that, the current must increase on the primary side of the CT, so that because it is an external fault, it must be nullified. So we will have this IC on the primary side, then whichever is IC is affected because of that. Now you will see that IC minus IB. So it is increased. So on this side, we will have the IC is increased, and finally it is increased in proportional to this, and finally we have IC minus IB here and IC minus IB here on this side. It is also increased. Similarly, we will have IA minus IC. So if this then it is IC is there, so IC is increased in that very case. So as a result, it will also be increased. So IA minus IC is balanced by IA minus IC, and IC minus IA is balanced by IC minus IB and is balanced by IC minus IB, and no spill current is flowing during the external fault. So as a result, our this differential protection is working well in case of external fault. So this is the case of the external fault. Now we can discuss the case for the internal fault. What we do in the internal fault, instead of this, we will have the fault here, somewhere here. That is within that zone of protection. So same fault is there, then fault at phase C. So fault at phase C, so this IC is increased, then this IC is increased. Now, since the fault is that at this particular point, you will see it. So this CT, this 3 of the CC does not see it because it is within the periphery of, it is inside that CT. So because if the fault would be there, then the current would be increased. However, fault is here, then this current is fed by here. So this CT is not seeing it. Now, on the primary sides, in the IC fault is there, it is feeding that. So it is increased, the value is increased as in the previous case. So we will have the increased IA minus IC. Then similarly, we will have the increased IC minus I A and there is no increase in the current on this side. So extra current will move to as a spill current, and as a result our relay will operate. So this is how for the internal this fault our relay will operate, and this is the all about the differential protection. What we have done in the differential in the protection system, we have first discussed the overcurrent relay. We have discussed the overcurrent relay. Then after that, we have discussed the differential protection. And in the differential protection, what we have done, we have seen that how we mark the different currents, and on the if we have let us suppose delta star transformer, then the CTs that are connected in that should be secondary of the CTs should be star and the delta. In that very case, the system will work perfectly, that we have discussed in these two cases. This is about the differential protection.